Greetings, Algebra 2 students. Today we're going to begin a new discussion on a different type of graph that we have not seen yet before. This is unit number 7, and unit 7 is all about rational functions. Our objective for this day is to acquire basic properties of the rational function. As always, press pause anytime you need more time to copy things down, and then press play when you're ready to move on. Now let's begin. All right, as we already said, today we're going to begin looking at a new type of function. Now, we call this the rational function. Okay, now a rational function is named after the structure of its equation. In order to be rational, there must be a ratio. And of course, ratios are built out of expressions that are in the numerator and expressions that are in the denominator, and typically those are in the form of polynomials. Those polynomials may be monomials or binomials or trinomials or even larger number of termed polynomials. Okay, but the point is we will be dealing with a ratio of two polynomials. Okay, so just to give you a little bit of a visual on what that means is we may be seeing equations that we're going to be graphing that may look something like these. Okay, so scribble those down. Now, there are a couple of requirements that a function must meet in order to be considered to be rational. Okay, now in order to be rational, there's a couple of restrictions on the denominator, and one of them is that the denominator must have a degree of 1. And in plain English, what that means is there must be a variable. Okay, if you have a degree of 0, then that would simply be a constant. Okay, being divided by a constant does not necessarily or technically classify something as being rational, because that constant a lot of times is absorbed by the terms that are in the numerator, and a lot of times you don't even end up with a fraction anyway, so it would not be considered to be rational. So you have to have a degree in your denominator of 1 or higher. The other thing that absolutely must be true in the denominators, and this is nothing new all the way back to elementary school, your denominator must not be allowed to equal 0. Now, as we've already discussed this year and will continue to discuss, when the denominator equals 0, something actually happens in the graph right there. And we've even learned to classify that thing. We have named it and learned to interpret what the graph should be looking like as that happens. And we'll get more into that as the days go on. Okay, but the two requirements, the degree of your denominator must be at least 1, and the denominator must not be allowed to equal 0. All right, now we have a parent rational function, which, as you can probably have guessed, this is the best place to start. Let's figure out what it's supposed to be doing so that later on we can figure out what all changes are going to happen when the equation starts doing different things. Now, the parent rational function is expressed very simply like this: y equals 1 over x. Now, another way that this is stated is by reciprocal language, as in y equals the reciprocal of x. Okay, remember the reciprocal simply means turned upside down. So when they say y equals the reciprocal of x, they are saying y equals x, and that fraction has been turned upside down, the reciprocal of x. Let's take a quick look at its graph. Okay, this one will be new for you. Chances are you have not seen or ever generated a graph that looks like this. Okay, but there is your parent rational function. We've talked about a bunch of different parent functions this year, but this is one that we have stayed away from a little bit, and now it's time for us to have a look at it. As you can see, the graph exists solely in quadrants 1 and 3. And the origin acts very much like a center of the graph. And actually, this particular shape of a graph has a name. It is the rational, apparent rational function that generates it. But this shape, where you have these two matching curvatures going away from each other, is what we call a hyperbola. This is another one of the topics that we will ultimately call a conic section later on in the year. Okay, but that's a different discussion altogether. Okay, now the parent rational function has two asymptotes. Now, we've mentioned asymptotes throughout the year, a little bit here and a little bit there, so chances are enough people probably are unfamiliar with them enough that it's probably a good idea for us to get a definition again. So go ahead and jot it down. Recall that an asymptote is an imaginary boundary that a graph will approach but not cross. Now, that doesn't mean that the graph runs directly at an asymptote. It just refuses to run into it. Okay, it actually turns along this imaginary line, runs alongside it, and basically gets closer and closer and closer to it as the graph goes to infinity, but it will refuse to ever cross it. Okay, it seems like a little bit of a contradiction in terms. If something was going to get infinitely closer and closer and closer, you would think it would eventually actually get there, but it doesn't. Okay, so that's the nature of an asymptote. And if we look back at the graph that we were just seeing on the parent rational function, okay, you can see that there are actually two asymptotes that are inherent to the parent rational function. Okay, in its standard position, there is a horizontal asymptote that passes through the origin. Okay, and remember that a horizontal line has an equation that reads y equals, and then you need a number that says where it crosses the y-axis at, which in this case is 0, passes through the origin. And also, you have a vertical asymptote that also passes through the origin. And of course, vertical lines have an equation that read x equals, and we need the number that tells us where does it cross the x-axis. And again, that is at the origin, x equals 0. Okay. Now, let's talk domain and range for a moment. Okay, it's important to understand how the graph behaves and where it has breaks in it. Okay, and since there are asymptotes in the graph, then that inherently means that our domain and our range are going to be broken as we travel through the graph. Okay, so in basic English, what the what the domain is doing is the graph proceeds from negative infinity. So at negative infinity, we do have one of the legs of the hyperbola all the way out there. So we're proceeding from negative infinity. We will continue all the way across the negative side of the x-axis. The graph will turn. It will move along the y-axis, never actually reaching the y-axis. That's why there's an asymptote at the origin. So we're going to have a break at the origin. But right at the other side of the origin, the other side of the hyperbola will proceed from infinity in the opposite direction and start moving along the positive x-axis. Okay, so the domain resumes on the other side of the origin, and then that side of the hyperbola proceeds to infinity. Now, there's different ways to express this, so I'm going to show you a couple of the more common ones. Okay, this is probably the most simplistic way of stating it, simply to give two intervals indicating where the legs or the sides of the hyperbola exist. We have one that in the domain comes from negative infinity to 0. We have parentheses around both the negative infinity and the 0. Remember, infinity always gets parentheses. Okay, infinity is always treated like it's open. Okay, and the graph will never actually reach the y-axis. That's why it's an asymptote. Okay, so we give the 0 gets an open parenthesis as well to indicate that the graph will never actually touch the y-axis. Then, on the other side of the y-axis, we come from 0 again, and this time move off to positive infinity. So 0, comma infinity, both of them open. Okay, 0 because it does not touch the y-axis, and infinity because infinity is always open. Okay, that's one way of doing it, probably a common way. Okay, a little bit more advanced notation that we're liable to start seeing a little bit of reads more like this. Okay, we have curly braces, which means there is a set. Okay, we're about to announce an answer, and that answer contains many values in it. Okay, now you see the little vertical line inside of the curly braces. Okay, that vertical line in there is pronounced such that. Okay, so this actually says the set of all x's such that x is not equal to 0. Okay, again, the set of all x's such that x is not equal to 0. You might want to write that language down next to this little expression. Okay, and basically what it is saying is that all x's are fair as far as the domain. They are all reasonable values except for the value x equals 0. So it's a little bit more condensed way of writing, especially when you have multiple intervals like we do in this case, and there's just one little value that is excluded. Okay, a little bit more condensed, a little bit more advanced way of writing it, and you're going to start seeing this notation a lot more. Okay. The range, okay, as you probably could recognize already, the range behaves the exact same way as the domain does when it comes down to the rational functions. Okay, so again, we could make the exact same statement from the range. It would come from negative infinity to 0. 0 is not included, but then the range would resume on the other side of 0 and then proceed on to infinity. And we could use that set notation. Okay, the set of all y values such that y is not equal to 0. Okay, one final thing to take a look at before we leave this alone. Now, obviously, there's a lot more information coming in future days. We're just trying to get familiar with the basics of the function at this point. And let's have a look at its inverse. Okay, now hopefully we are learning by now that the idea of an inverse simply reverses the variables within that equation. So the x-axis essentially becomes the y-axis becomes the x. And of course, the direct translation of that is that the graph is reflected through the line y equals x. Well, let's take a look at that inside of this graph. Okay, so we're going to take the rational parent function and we're going to perform its inverse. Okay, now the equations look very, very similar to each other. Y equals the reciprocal of x and x equals the reciprocal of y. Now have a quick look at some sketches of the graphs. Doesn't take a real rocket science to look at the two rocket scientist, pardon me, to look at the two graphs and determine that, hey, they are identical to each other. Okay, and this is one of the rare occasions in mathematics where an entire graph is actually its own inverse. Okay, so when you reverse those values, sure, x comma y is going to become y comma x, so the points may not look the same, but there will be other points from the reversal of values looking at the inverse. So points may move, but other points are going to take their place, and you end up with the exact same graph graphed twice. Okay, that's enough information for today, just getting us started on the rational functions. So I appreciate you finding time to get your notes taken care of, and I'll see you in class.